Hi, everybody. So I'd like to go over some attenuation and half-life type problems. So let me just start this. So it's just taking a minute to start. I don't know. Okay, so I wanted to go over the difference between half-life and linear coefficient of X-rays. So when we're talking about half-lives, we're talking about how many photons are attenuated to half their original quantity, and that's called half-value layer. So for instance, if we have 100% of photons that are going through a material, then the amount of material that would reduce them to half their intensity would be half-value layer. So as photons pass through a material, the photons are attenuated or reduced. And there is always an attenuation of photons as it interacts with matter. And attenuation, the amount of attenuation depends on how thick the material is. Also, the atomic number of the material. So by definition, half-value layer is the thickness of an absorbing material that's necessary to reduce the X-ray intensity to half of its original value. So we typically express half-value layer in terms of millimeters of lead, let's say, for an example. The higher the energy of the X-ray beam, the deeper it can penetrate. So the higher the energy, the more it can get through the material. So here's the picture, and it's showing a bunch of photons here on the left, and this half-value layer is going to reduce the number of photons by half. So you can see the intensity, which is another term for number of photons. So attenuation is the reduction of the X-ray intensity resulting from absorption or scattering. So low energy X-rays are more easily absorbed than higher energy because the higher energy photons have the ability and the energy to pass through a material. So some technical factors that will affect the half-value layer are KVP, which controls the penetrability or the average energy of the beam, and filtration. So what filtration does is it filters out the lower energy photons, so you will have just the higher energies photons that are able to get through. Distance and mass will have no effect on radiation quality. And quality, again, is the energy or the penetrability. So the penetrability, when we're talking about what can get through a half-value layer, so if we don't have a half-value layer, let's just say on this little table right here, if we do not have a half-value layer at all, nothing's in front of the beam, then 100% of the photons will be able to get through and nothing would be attenuated, right? If you have one half-value layer, then 50% of the photons will get through and 50 is attenuated because a half-value layer is reducing the number of X-ray photons by half. If you have two half value layers, that means 75% have been attenuated and 25% are transmitted through, and so on and so on. So this is the difference between transmitted, what is getting through, and what is being attenuated. And this graph is nice too. If you have one half value layer, that means 50% of the photons are being transmitted and 50% are being attenuated, unable to get through. If you have two half value layers, then we're taking 50% of the 50%, so 20% are able to be 25% are able to be transmitted through, and 75% have been 25% have been transmitted and 75% have been attenuated. And then you can see this is, one half value layer, two, etc. And this is basically the same type of diagram. You have, let's say you have 1,000 X-rays that are incident, and then as they pass through the layers of tissue or the layers of a substance, they're reduced by half. So one half value layer in this example is 4 centimeters. So if it goes through that 4 centimeters, which is one half value layer, the X-rays would be attenuated by 500. If they go through 2 half value layers, the X-rays will be attenuated to 250. So like radioactive decay, X-rays are attenuated exponentially, which means they are reduced in number by a certain percentage for every increment thickness of tissue that they happen to pass through. So if we have an energy of 120 keV and the length of the material is 1 centimeter, okay, and each half value layer is 0.2 centimeters, okay? So after one half value layer, we would have 50%. After 2 half value layers, we would have 25%, etc. But if we need to find out the half value layer of a more complicated amount of a thickness, then we need to use a different, we could use a different formula, which is similar to the activity formula. So as X-rays go through a material, as we said, the intensity is going to decrease. So this formula is very similar looking to the activity formula. It's the initial, it's a final intensity equals the initial intensity. And then this is the attenuation coefficient, and X is the amount of material. We'll get back to that formula in a minute. So X-rays are attenuated as they pass through tissues and matter, as we already discussed, and we can calculate X-rays as they pass through a set distance of tissue, and this is done by looking at the linear attenuation coefficient. So what the linear attenuation coefficient looks at is the number of X-rays that have been removed from the X-ray beam. Okay, so it's the ones that aren't getting through. So we look at X-rays that are attenuated and scatter as opposed to transmitted. So the linear attenuation coefficient determines the rate that X-rays are being removed. Okay. And it's a combination of the photoelectric effect, the Compton effect, Compton scattering, and coherent scattering. All three make up the linear attenuation coefficient. So the atomic number and the tissue density, as they increase, the likelihood of the linear attenuation coefficient, or the what's the word I want? Or the photons not being attenuated will increase. Okay, so these three materials will determine the likelihood of photons being attenuated. The density of the material, the atomic number, such as a high Z number, such as bone or metal, and what is the incident photon energy, because higher energies will be transmitted more than the lower energies. So here's a graph that shows the attenuation of X-rays as it travels through a set distance of tissue. So on the y-axis, we have the number of photons, and on the x-axis, we have the distance. And notice that initially, we get a great reduction in the number of X-ray photons as we travel through the tissue. And the absolute number of X-rays that are removed from the beam gets smaller and smaller. However, the proportion of X-rays that are removed always remains the same. So here's an example. Here's, let's say we have 12 photons, and it's going, let's say, one distance. Let's say it's, I don't know, 1 centimeter. And so as it goes through the distance, then X-rays are being attenuated. And the photons will continue to half as we travel through set distances. And the distance required to half the X-ray photons is called the half-value layer. So in this graph, notice that we initially have 12 photons right here. And when we travel a set distance, I don't know, let's just say it's a centimeter, we now have 6 photons. When we travel the same set distance, now we have 3, et cetera, et cetera. So N is the number of X-rays that remain in the X-ray beam, or the number of photons that are left in the beam. N is the original number of photons. Negative mu x is the linear coefficient and the distance. So it's the linear coefficient times the distance, which is x, that it's traveled through the tissue. And the higher the linear coefficient, the more dense or thick the tissue would have to be, and it would result in a lower half-value layer. Okay, so here's the formula. You can use I, or sometimes you see it as N, so I'm just using I here. So here's the final intensity. Here's the initial intensity. Mu is the linear attenuation coefficient, which tells us how much attenuation has occurred over 1 centimeter. And X is the distance that the photons have traveled across the material. So we need to put the attenuation coefficient should be in centimeters. And it is a universal constant. So it's 2.71. Okay, E doesn't have any units. So just like how the half-life problem, it was a constant of 0.5. This is just called an E. And we use that here instead of the 0.5. And why is it negative mu times X? It's just, we use negative to indicate that it's an exponential decay. So I'm just showing you the difference here between the activity half-life problem. So A activity, final activity is initial activity times 0.5 to the n, where n is the number of half-lives. And to calculate the final of the number of half-lives, you need the time and the half-life of the isotope. So this formula tells us how much activity has been reduced when the radioisotope decays through some period of time. Okay, and attenuation problems, such as the one below, where mu, or the linear attenuation coefficient, tells us how much of a photon beam intensity is reduced when it travels through a distance. So to figure out the half value layer is the natural log of 2, or 0.693 divided by mu. So if we're giving that a half-life, if we're given the half-life and then we want to know what mu is, well, half value layer is 0.693 over mu. So it would be 1.2. So if we had to figure it out, oh, let me see, sorry. We had to figure, if we were given the half value of a substance is 1.2, then we would say, well, the formula is half value layer equals 0.693 over the linear attenuation coefficient. So they told me it's 1.2. Half value layer equals 0.693 mu. Okay, so then I could just multiply mu times each side. Okay, and then I have mu times 1.2 equals 0.693. So then I would just take 0.693 divided by 1.2.